UAVs and micro UAVs especially, and how can we solve those with the less computational capability. So yeah, besides that, I have worked with the definitely, like I said, on Hyperloop. And initially it was more about the multidisciplinary design optimization, designing the wheel system. And later on, when we won one subsystem innovation award and came back from the competition, then we got to work as a big group for overall looking into the power system and all those. But yeah, I'm not actively involved in Hyperloop as of now because of well, various other conditions, like focusing on the dissertation itself takes a lot of time. Anyway, so beside that, here in Canada and in university, I got a lot of other opportunities, like working on the something called battery management system, and then something to work on the machine learning aspects, and a lot of other side projects which were really exciting. So yeah, without further ado, I'm gonna just jump into this topic now. So overall, I'll be talking about the UAV use cases. I guess this is almost all of us, we know what are the use cases of UAVs. And then in particular, I'm gonna talk about the problem of rapid trajectory generation on fixed wing UAVs. So this is one aspect of one chapter of my PhD thesis. There are other 5 chapters. So I'm just going to focus on this topic. And as soon as my thesis becomes live, meaning that the university shares the link to the general public, you can look into most details. And then if you want to try something out, you can definitely go ahead. So yeah, well, we might have just a little bit of history that when I was kids, the drones were popularized by the US military, and then I could see a lot of news and like drones did this and that, right? And then in recent days, the quadrotors from the DJI are widely used among consumers, and because of its photography, videography kind of thing, it has been really popular. Besides quadcopters, there are a lot of other UAV types that has been tested or still being tested, and fixed wing, and then we call combination of both, and various other types actually. There's something called bicopter as well, and a lot of them. Today, so most importantly, today I'm going to talk about the fixed wing UAVs, but anyway, these quadrotor and fixed wing UAVs are again really popular for like a delivery, this application in delivery, like a drone as a delivery, and big players like Google and then Amazon, they are working towards making it happen sooner. So one of the example, this is just a bit of example, is the UAV for DHL by EHang. And EHang is a Chinese company, and they have made, I think they were really popular back like a couple of years ago when they made autonomous passenger carrying drones. And they are partnering with DHL to make the drone delivery possible using this quadcopter. This is a really good example. And this is the drone for UPS by Wingcopter. This is a fixed wing design, and definitely will come. I guess it will cover longer ranges than the quadcopter. And this is one good example too. And this is UAV by X-Wing. They have already started delivering coffee from local coffee stores to the public. The remote, I think I forgot the name of a place. It's somewhere in remote parts of Australia, I guess. Maybe Sudhita knows more about it. And I like this example, and not only because of its application, also because of its range. And I've heard that they have already are capable of delivering the parcels up to 120 kilometers, which is really good thing. So yeah, beside that, those were the drones examples. And beside that, people have been working on the virtual roadway system, especially for the urban area, like city-like environment, where there are certain regulations that you cannot fly above certain regions, and you want to avoid the the crowded space, you want to avoid the tall buildings and things like that. So the companies like the AQUARIUS are working towards making this possible, that there's a fixed roadway system in the sky, and then the quadcopter, or I suppose quadcopter will be able to fly in this specific road. and then deliver parcels to the door. And the second company, there are many of them, but the second example is Airmetrics. So as the company says that, like, it builds a 3D network of drones road and drone roads with industry leading millimeter precision. We'll see what the industry has to offer. And the good thing, I mean, the thing I really like is that the drone operator usually would request route by inputting the starting and endpoints, and then the drone will fly, remaining as close as possible to the route. This is really exciting. And this is something similar I have done as part of research. So the motivation for my research was to serve a fixed-wing UAV for autonomous geophysical survey. This survey has to happen in like a poorly known terrain, meaning that you do not know much information about the terrain, and also like you want to survey the large area, so definitely the UAV might be out of sight, and you want to capture like a high quality survey data, so you want to be flying really low, meaning like low altitude from the ground. So such kind of application where we are flying really low, and then there's a chances of a lot of obstacles being detected. And oh, just a second, and my research is not on detection side, it's more on developing the avoidance side. So given there's good detection methods like let's say stereo vision or some other technique on board UAV, then flying and avoiding obstacles and doing the survey at the same time will demand that the when the new obstacles are like seen, you want to be avoiding the obstacles and then going back to the survey path again. So here is an example. So suppose this is a UAV, right? And then there are obstacles like trees and let's say power lines or certain water tower or certain structure. And once like you avoid these obstacles as a tall trees and something like that, then you want to be going back to the track in order to collect the high quality survey data. So you don't want to be deviating from the line, you want to stay on the line, but when obstacles comes in, you want to avoid and then go back again. So this kind of, I mean, this approach is actually also applicable like if you have a roadways, and once you avoid obstacles, you want to go back to your roadways again so that you reach the destination, right? So this kind of application demands the rapid trajectory generation, and especially on board the UAV, because we're not controlling from far distance. And controlling the UAV, rapid trajectory generation, because for fixed wing UAV, like there's really a less time to react. Like when you see the obstacle, then you're flying at the minimum velocity, let's say 10 meters per second or something like that, and at that speed you want to be avoiding obstacles, right? So you need some trajectory generation system which is real quick, and you want a real good computation capability. And though there are really good computers these days, having the algorithm that guarantees this at least sub-solution time, or at least feasible solution with given amount of time, is really important. So yeah, I'll talk about, this is a really high-level picture of how does the control architecture for UAVs looks like. Like we have a mission objectives, and then when you say objective, like you have a cost function or the objective function. Let's say you want to reach the goal point, you want to remain close to the path, and I'll discuss about this thing a little bit later on as well. And constraints are like UAV's control constraints, like the rate at which the flap can change, the rate at which we can increase or decrease the RPM of the motor, of the propeller's RPM, right? So, and the map of the environment. Sorry. So all of these things come under the mission objectives, and you want to force that altogether problem into the trajectory generation block. So you have everything mathematically defined and kept inside, or define that as a trajectory generation problem. And once the trajectory is being generated, you want to send that to autopilot, and autopilot will do a low-level control loop, meaning that sometime, like most of the time, I think almost all the time, sorry. So there is a low-level control loop going from autopilot to the UAV's control system, and the servo motors and the EACs, I mean electronic speed controller, and that will control the RPM of motor. And then definitely there are sensors that will update the state and also the environment information, and that update will be, sorry, that will be updated again back to this real-time trajectory generation block, and this has to happen real quick. I'm saying real time, so it will be something like real, like online, when you say something like maybe in a matter of like tens of milliseconds. So when you say hertz, like 5 hertz means that 5 times in a second. So we're looking for something above 100 hertz, or maybe even 1000 hertz is really good. Definitely is better, right? So this has to happen every sampling time. Sampling time, like meaning let's say the sampling time meaning like 1 millisecond or 10 milliseconds is sampling time, and we want to be generate trajectory at the speed. And this trajectory generation problem, which is the mathematical formulation of the mission objectives, is a nonlinear programming problem. So I'll talk about that a little bit soon. So overall, my main research focus was on this block, so real-time trajectory generation block. So if we could just figure out this thing to be able to solve in real quick, then all of this thing, having all of these blocks will be meaningful, right? So, and one more thing is that this trajectory generation problem gets complex with UAV's dynamics, and then if you have more obstacles, then the more complexity, more number crunching to do, like no more numerical computation to do. And generally, we use a nonlinear programming algorithms to solve this nonlinear programming problem, I said, this trajectory generation problem. And there is no guarantee of convergence within the sampling time. So, like if you use the general solvers, there is no guarantee that you can solve within a given amount of time. So you have to do, you have to take a different approach, like trying to customize a lot of other things. But we need the low computation time, and that has to be happen on board computers, not the big end computers and the rest of computers like that. And if somebody might argue that, what if you generate a trajectory on a desktop computer and then send over network? So for those, like there are a lot of examples online that people have been trying it, and we know how the like telecom towers and the signals has been are distributed. And to make use of it, I think it'll be like for large distances where there is no coverage, is almost no. And unless you have your own communication protocol and then own certain set of communication signals and certain towers to be able to send signals that far, right? So yeah, so those of you who are not familiar with this nonlinear programming problem, just an example. You have an objective function fx. Let's say you want to minimize this function, and you have a constraints like inequality greater or equal to 0 constants and equal to 0 constants. Like this could be, let's say, this is a function that you want to minimize, given that some expression here should be greater or equal to 0, and some expression should be equal to 0. And all the solutions should be within the given search space. So that's how the general nonlinear programming problem looks like. And this is also a nonlinear programming problem, but you have search space in a real number, and this is a cost function you want to minimize in this search space, right? So it's really a simple example that the minimum of this would be definitely x is equal to 2 and y is equal to 4. Well, if you are working with this kind of equations, then you can definitely figure out what's the minimum of this function. Where is the minimum of this function? So at what value of x and y will this function be minimum? So yeah, you can see a plot, a graph of it, that the value of x will be minimum at 2. Value of the functional minimum will be at x equal to 2 and y is equal to 4. Beside that, there's increasing value. So there's a next, like a little bit of quadratic programming problem example with constraints. So you want, suppose the objective function is that you want to minimize this function subject to this equality, both of them equality, and you are bounded by like lower and upper bound. So this could be good example for someone in the first or second year of undergrad if you want to solve, if you want to know how, what does this optimization problem look like, then you will first, you can make Haitian out of this, which is second derivative of the cost function. That's what we call it. And gradient is the first order derivative, and then you have, we call this Jacobian usually, which is basically arranging these matrices and this equation in a matrix, and that's the B inequality and the lower and upper bound. And like if you are using MATLAB, then you can use a quad program. There are a lot of other solvers, but you can. This is just one example of like this is Haitian gradient, and these two spaces were for inequality, and I don't have the inequality here, just the box constant Alexa, this lower bound and upper bound. And I haven't defined what V0 is. It is initial point or a starting point. And in this optimization, like starting point matters a lot. If you have highly nonlinear optimization, meaning that if you have really complex nonlinear cost functions and constraints, you could have a various, like, depending upon the starting point, we have a different optimal solution. We call it locally optimal solution. Anyway, so those are really basics. So I'm going to jump back to our approach of trajectory generation. So the trajectory generation problem, which is a nonlinear programming problem, we pose that as a control problem. Since we want to solve it as an optimization problem, then we call it optimal control problem. And that optimal control problem is a nonlinear programming problem. And nonlinear programming problem, like I said, there's no guarantee on the solution time. So we take the approach, the sequential convex programming approach. So meaning that we do a convex approximation of this nonlinear programming problem. The convex in a sense that, let's say, the cost will be quadratic and the constraints will be linear. So the quadratic programming problem with the quadratic cost and the linear constraints, and then we solve it using a custom solver. So when I say that, so most of us, and I mean, most of people, those of us who are not working on this optimization and who are not familiar with the solver may not know what does solver do. What does the solver does is basically it solves the quadratic programming problem that I showed earlier, like this. But the goal of this custom solver was to solve the problem real quick. And the way it's basically a general QP solver, but that has been customized, like for given a specific problem, meaning that anything like in a huge matrices, even let's say in AeSN matrix there are 2 zeros, so we don't need computation with zeros here. So something like that. When this is just like a 2 by 2 matrix, but when you have a 1,000 by 1,000, 2,000 by 2,000 matrices, then if the matrix is really sparse, meaning that there are a lot of zeros in the matrix, then we don't want to be competing with zeros, unnecessary zeros, right? So the customization I have done basically deals with only non-zero terms. So I want to show an example. I'm going to exit this presentation. I'm just going to come back again. So yeah, here, suppose A is a matrix here, and then one thing to note is that this is a symmetric matrix, and see you have at least like 3 zeros on the top and 3 zeros at the bottom, and there's a diagonal 1 element, 1 more zero. So, and one more thing, since there's symmetric matrix, there's a repetition of entities, right, in the above leading diagonal and below this leading diagonal. So what you can do essentially is you could actually store this whole like 16 elements 4 by 4 into something like this, only 6 elements, A, B, C, D, E, F, and then you could multiply it with a vector. And this is your custom matrix and vector multiplication program. So that's how you try to lower the memory requirement. And also most of the cases, this is really good for embedded application where you want to speed up the computation. And but like for maybe the this may not be always great for all the computers, but for if you want to work on a low memory platform and the low computational platform, and this is really useful. And this is what these are the computers generally that we can keep on board the micro UAVs. So that was the motivation for doing this. So I'm going back to this presentation again. Yeah, and so overall, so now we jump into the topic. The objective of this study was basically to study the rapid trajectory generation and autonomous obstacle avoidance for fixed wing. And though I have written quadcopter here, and that was a part of the study as well, but I'm just presenting on the fixed wing. And up to the immediate window, meaning that like we don't want to be, so this is something that if you have a starting point and a goal point, and if you want to generate a trajectory numerically, then you have a discrete node points in between them. So when the distance between the initial and the goal points are really far away, then you will have really coarse like points distribution. So you might, like, there's a high chance that you might skip obstacle in between when the node points are really far away. So I'm taking the approach of finite horizon trajectory generation problem. So it means I will I'll solve for the finite horizon, let's say 6 seconds in future, or let's say we can even choose the distance, I guess, and then 6 seconds or 12 seconds in future, and solve. That's just for the immediate window. Like, we don't want to be solving all the goal point. But the issue with this is that you may not, like, if you don't have an end goal point, then there is no motivation for UAV to progress ahead and reach the goal point. So to deal with that, imaginary goal plane, which is perpendicular direction of flight, has been introduced, and I'll talk about that a bit later on. And the UAV has to remain close to a desired flight path while avoiding obstacles. And I solved this problem within this MPC framework, meaning that you have a UAV model, and then I'll try to like predict, basically try to linearize the model at the discrete node points only up to the finite horizon, and solve that finite horizon trajectory generation problem using the QP solver. And for that, I'll use a custom solver. And at least the hope is that we can solve that within every sampling time or given sampling time. So for those of you who are interested can definitely dive into it. This is a point mass model of fixed wing UAV, considering thrust here and then drag and then lift. This basically is the XYZ position in 3D space, velocity, and this is the flight path angle and then the heading angle. And again, this is a linear constant that has been added to actually prevent the bang-bang controls we call in optimal control on alpha, phi, and thrust. So this limiting the rate how the alpha, phi, and thrust changes. This is the alpha is angle of attack, phi is the roll angle, and then thrust is definitely thrust. And these are treated as control inputs to the autopilot. So once autopilot accepts this, then it will generate a low-level controls signals to the servos so that the UAV can fly along the given trajectory. Basically, this is what we call dynamic constants of UAV, and this could be a certain values, and this omega alpha, omega phi, and TR, the thrust rate. There will be a bounce on how much they can change. So, and one more thing, there is a wind conditions here that it has to account, like what if there are wind disturbances, right? And then in that case, how can this model predictive control within this finite horizon approach can compensate for that? We're going to look into that. We're going to look into that as well. And the trajectory planner has no knowledge of the wind field. So this is an example of dynamic model, point mass model of fixed UAV, and this is a kinematic model. Here, few things are fixed, like again, this XYZ space, 3D space, and the flight path angle, heading angle, and velocity. And these are the rate at which those heading angle, flight path angle, heading angle, and velocity changes. And again, this control constant has been constant further to avoid the bang-bang control again. And here we have a bounce on how much like the UAV can turn. So the few things have been constrained here in this kinematic model, and when we will compare like which one is better. Definitely having a complex dynamic equation, it takes a longer time to compute. I mean, it might have but generally the thought is that if you use general solvers, then this might take longer time to converge, whereas this should be converging quickly because of complexity. And we just want to compare how does it, what happens if you customize, and then what are the advantages and disadvantages of these two models. I mean, pros and cons of these two models. So this is my overall cost function. So now in red, like I said before, let's say the UAV is flying along the y-axis, positive x-axis, positive x-axis. Then xt is equal to xa is a goal plane. That's where I want to reach. And so my aim is to minimize the difference between the current x position of UAV and the goal plane xa. X is equal to x equal to xa. So I want to find the I want to minimize this like a position minus the goal plane. So that becomes my one of the cost function. And I want to remain close to the y-axis. Y is equal to 0 all the time. So exactly on the in the abscissa, abscissa, I guess. So anyway, along the x-axis. So that's why I have a I want to stay on y=0, so there is no constant added. And here I want to stay on the height JD. Like I want to, let's say JD is 60 meters, then I want to make sure that my Z position, this Z is X, Y, Z are the position of UAV, and I want to make sure that the UAV has a certain height JD, and I want to minimize the error. So if I'm deviating, I'm with 70, then I want to go back to the 60 again. And this is a robustness function. It is something you do with obstacle. So what happens in this, I haven't kept the equation here. So what happens is that when you are at the vicinity of the obstacle, or at least like the presence of obstacle, not even vicinity, in the presence of obstacle, that the value of the robustness will go higher. So you, in order to minimize that, you have to be far away from the UAV, and that's how you avoid obstacle. And this is the penalty parameters like a eta, alpha, beta, and then WTT. So this is the penalty parameters, like how much priority do we give to obstacles? I mean, like it depends on how far we are from the obstacles, right? So I mean that will be a ideal condition. So suppose you have 20 obstacles, and if 20 obstacles are affecting your trajectory generation all the time, then that is not something you want to account. All the obstacles, that those are really far away. So you want to be only taking those obstacles that are nearby, and you want to avoid them. So if the obstacles is greater than RB in distance, then the impact, the GT basically will be 0, making this WGT 0 as well. So meaning the obstacle will have no impact on the trajectory. When the UAV reaches near the obstacle, then that's how the weights, the GT increases, and then when you are really near the RA, when you reach the RA in distance, then the impact of the obstacle on the UAV will be maximum, and the UAV is forced to avoid this obstacle. I mean, given that the impact of this robustness factor or robustness function will be higher than compared to any of these. So usually, like one thing to note here is that when the X is really far, then the value of this at the starting point will be really high. So you want to be keeping this eta really low, and the one stops and then definitely there are certain things, pros and cons, that this is something crucial as well, like when you are avoiding obstacles. I'm going to talk about that a little bit later again. So yeah, so overall this is my cost function, and this is the problem, that we want to find, like given the initial condition or the initial position of a UAV, we want to find the state control pair, meaning that the trajectory and the controls required for UAV to fly along the trajectory. Given the, we solve the two different cases, like using a dynamic equation and controls, states, and obstacle constraints. So you have a constraints on how much this X, Y, Z, and then flight path angle, heading angle, velocity can range, along with this angle of attack and roll angle and thrust. Similarly for the kinematic model as well. So these are the two different problems. Same objective, I mean same cost function, but two different constraints for dynamic and kinematic, and we're gonna compare these things. So yeah, we're gonna jump, and then yeah, this is the UAV, the AeSN UAV. This is a really lightweight UAV, like only a little over half a kg, and density is like, it is the density, sorry, and then the wing surface area is 0.2135. A few things to note here is that the minimum for such UAVs, like minimum drag coefficients and then the OSWAL efficiency, are not really available. So this was based on the paper by Ananda, I guess. There's no paper there, John paper, and I the study on the micro UAVs, and these values were assumed based on the plots from there, are basically propagated, and then these values were assumed. And yeah, all the results in the slides are for this AeSN UAV, and I think you may be able to see a lot of details on this UAV in the specific paper. I can share that slide later on. Sorry, the paper later on. So this is the trajectory comparison between dynamic and kinematic. The red is the dynamic one, the blue is the kinematic, and there's a one the reference path that's going along here, the straight line. So basically the UAV has to fly along this straight line, at the same time has to avoid the obstacle, and there's a wind condition like 20 km/h wind in between this region, and at the same time there's a moving obstacle. So how would this dynamic and kinetic model behave? So this trajectory shows that the modal predictive control, the finite horizon modal predictive control, and the solution that it can generate, or the optimization problem that it has to offer while solving that using the custom solver. And that's the direction of flight. Sorry, this is not clear maybe. And this is around this stationary obstacle region, and you can see how the dynamic model behaves, and the kinematic model deviates a bit while avoiding the stationary obstacle. So maybe it is obvious because dynamic model is supposed to be better than kinematic model. However, there are other pros and cons as well coming with the dynamic model, which we're gonna discuss a bit later on. Again, this is around the moving obstacle. Maybe it's not visible. This is a small dashed line, red line, brown line, sorry. And this is the wind region, and this is how the trajectory looks like. So I have removed the obstacle from here, from the plot. So you could see how the dynamic model stays low and then come back to the reference path as soon as the obstacle is avoided. And here is an example at the different position stems. So at axis equal to 860, that the UVs know that the obstacle is here, and then by the time, I have skipped some time steps in between, and by the time the UV reaches 910, the obstacle is still here. And then by the time the UV reaches 930, the obstacle has almost passed the obstacle region maybe. And then one more thing, the obstacle is supposed to move along the straight line. And by the time the UV reaches here, the obstacle has already been avoided by the UV, and you can see how dynamic model quickly tries to go back to the reference path, and then try to follow the line here and try to reach the reference path here, and the dynamic model catches up that definitely. So one more thing that I'd like to just talk a bit about here is that about how do you choose obstacles? I mean, how do you choose where the obstacles comes from? If obstacle is coming head on, and if your obstacle is coming from sideways, and then like what are the velocity obstacles, all of them definitely matters on obstacle avoidance, and how much of the constraints you want to handle, how much of the disturbances, what types of obstacle you want to handle. Everything can be incorporated into this problem formulation, and then we can solve it. And even if the obstacle is coming from behind and trying to hit your UAV, and at that point, even for such condition, depending upon the nature of UAV, you can model the problem and then put that into a trajectory generation block, and then generate a trajectory, and the UAV should be actually able to, given we do not violate, we understand the constants properly, then given the simulation result shows that it can do it, then it should be able to do that in real life as well. So this is the computation time calculation in the Intel processor. So it's my laptop computer. So yeah, the flight time is a little above, I think 125, 126 seconds, and this is a computation time in milliseconds. So, in the laptop computer, definitely we're not going to put this laptop computer on board the UAV, and this is just to see what are the computation time using the custom solver again, not with the general solver. Those of you who have done optimization better knows what is the solution time of optimization problem using the general solver. So yeah, and this is the statistical results. We shows that like among the 100 of the test scenarios, when there are 20 obstacles and the finite horizon is 6 seconds, meaning we are generating a trajectory of 6 seconds in future every time we progress ahead. And we have a control horizon of 0.2 seconds, meaning that the sampling time and control horizon are same in this case. I'm not going to talk about this control horizon. So yeah. Most of the cases, like more than 90% of the cases in dynamic model, we are able to solve within 5 to 10 milliseconds, and then kinematic model, more than 70% of them are solvable within 10 to 15 milliseconds. And again, this is not much of a difference, I would say. But in terms of cost, the kind dynamic model is definitely better than the kinematic counterpart. So here, the idea is that, I mean, the result shows that if you could get a better result with dynamic model with the relatively same amount of time with the kinematic model, then why not we use a dynamic model, right? And definitely using a custom solver. So that is one advantage, like I see with the dynamic model in the study. And this is the solution time computer in Raspberry Pi 3B computer. So if any of you are familiar with this Raspberry Pi 3B, then definitely you know what is the size. Basically, it's a credit card size computer. It looks like it is approximately, I think maybe the same size as that of the credit card. So I have never measured it, but yeah, that's what people say. So this is the solution time comparison between dynamic and kinematic model. You might see a little bit higher in the dynamic model. The one thing that the difference is that in MATLAB, the solution time earlier is in my laptop is within MATLAB, and it is being computed in double precision, and this is with a single precision in the ARM processor. So yeah, one more thing that could be interest to people is that to know that, okay, what is the, like I said, 6 seconds in future, we want to be able to generate a trajectory of 6 seconds in future, right? When the UAV is traveling at 10 meters per second, so 6 seconds in future is just 60 meters. So 60 meters in future, like, but what if like, so how do we calculate what is the required horizon? Like, how do we be able to calculate the required horizon of the UAV? Like, how far the UAV has to see to avoid a certain kind of obstacle? So this is a small analysis. Like, let's suppose at the point U0, there is a sensor on board, let's say stereo vision, and you can detect an obstacle at this point, and maybe delta TS time is the processing time for the sensor to say that, oh, there's an obstacle, right? And then once you are sure that there's an obstacle, then you have to avoid it. Then you pass that information to the trajectory generation solver. And let's say if that takes delta TC time to compute the controls, then you still need this RT radius for turn to avoid this obstacle. So definitely, if the obstacle is smaller, like this red box, then you may be able to avoid from U3, but the obstacle is really large, and then if there's a wall, then you want to make sure that you want to avoid the obstacles and turn around. So yeah, in this case, this is just a way of like how you could actually do a small analysis on what is the required range of horizon and things like that. This is for the stationary obstacle. And what if you have a moving obstacle? At this point, you can see really far. Suppose you can see like this much far and say, okay, there's an obstacle, and maybe, sorry, you detect a first glimpse of obstacle, and then U1 may be the point where you are sure, okay, there's a moving obstacle. Maybe not yet. You can just detect there's an obstacle, and then still like, sorry, let me say this again. At this point, U0, you will just get the first glimpse of obstacle, and then it might take up to U1 point to be sure there's an obstacle, but you at least need a couple of glimpses to make sure that this is a moving obstacle. So by the time you will be already computing one step ahead, and then just thinking this as a stationary obstacle, and the stationary obstacle, and then at this point you will again process and say, okay, realize that this is a moving obstacle. Of course, this is just one rudimentary approach of analyzing of how much of further you need to see to be able to avoid a moving obstacle. So once you know this is a moving obstacle, then you will pass that information to the trajectory generation block again, and then the trajectory will be generated to avoid the obstacle. So this is just a rough approximate how you may be able to do that preliminary analysis. So this is a little bit of, I mean, some results. Like, let's suppose the frequency of obstacle detection is 20 Hertz, meaning sampling time of obstacle detection is 0.05 seconds, and the UV velocity is 10 meters per second, with the minimum turning radius is 14.67 meter, and the velocity of moving obstacle is, let's say, 5.55 meter, which is coming in head-on collision with the UAV. Then in that case, when you have a solution time of 1 millisecond, and this is at least the minimum range for stationary, and then 37.44 is the minimum range we need to be able to see for a moving obstacle. And one thing to notice that I don't find any difference, like much difference in sensor range, required sensor range, from going from 1 Hertz to 200 Hertz, even 500 Hertz maybe, but there is a catch here. You could even try 200, like 2000 Hertz, meaning 2 seconds, if your sensors can see really far, but there is definitely a catch with this. Like, if you take 2 seconds, then maybe there are other environmental disturbances that that the solver may not be able to account, and maybe you need a real quick accounting of those changes in environment. Maybe 100 milliseconds is important depending upon the how much stable UAV is and what UAV is and what type of UAV you are using, right? So in our case, like 200 milliseconds is fair enough. Like having sensors to be able to detect obstacle, let's say 50 meters ahead in distance, is a good one, I guess. The stereo vision should be able to do that. And but the thing is that we have to be sure that we get a good sense of where the obstacles are. So this is one example on how we can determine it. And yeah, like I said before, there is a catch. So if you go with 100 millisecond, 1000 millisecond, 1500 millisecond, or even 2 second or 2000 millisecond of computation time, you don't get a flyable trajectory with that dynamic or kinematic. This is for kinematic model, and you see the dynamic model as later on. But yeah, you don't see the flyable trajectory. So even you see with the 1000 millisecond, you're not being able to even close to the reference path, which is along the y-axis, sorry, x-axis, at y is equal to 0. So the 500 millisecond or less than that. The previous examples were with 200 millisecond, and this is the test case. It's like what happens with 500 millisecond, what happens with 1000 milliseconds. It seems like you want to be within, you want to be solving problem real quick. You don't want to delay to be able to account the environmental changes. And you can see, at least with the kinematic model, this two of these roads are actually moving forward. But with the dynamic case, all of these three fails, and then only the blue, this green one with 500 milliseconds being able to progress ahead. And still you can see there's a flag a little bit, like when it's just waving around along the reference path. So dynamic model is better than kinematic, definitely better than kinematic model, but you want to be able to solve that problem with higher frequency, meaning less than, let's say, 500 millisecond, like 200 millisecond, if you can, 100 millisecond, to be able to get the good trajectory to be flying around. I mean, to avoid to fly around the obstacles and avoid them. Sorry. So yeah. Finally, this is something I wanted to mention ahead before about the penalty parameter eta. So what happens is that these penalty parameters eta, alpha, beta, and they play a vital role in determining like which cost function to prioritize in solving the problem. So when you are near the obstacles, you want to prioritize the obstacle avoidance. And when you are done avoiding obstacle avoidance, you want to prioritize and remaining close to the reference path and progressing ahead. So usually when you are at, like, XA is really far away points, then a small value of eta can play a significant role in progressing the UAV ahead in the direction of light. But when you are near the obstacle, the impact of the obstacle becomes so high that the impact of this, when the eta is really small, and then you can see this green and this black line, then at this point that the UAV may not progress along the direction of light and may actually turn back. It's because of the impact of this becomes really small, and then impact of this becomes really high, and you are only focused numerically, only focused on avoiding the obstacle. That's why, like, it's better to have this eta dynamically changed, meaning you want to be able to change the eta based on if you're near obstacles or far away from obstacles. If you're near obstacles, you want to have this penalty higher as well along with this. So that as long as you are avoiding obstacle, you are progressing along the direction of flight as well. You can see the eta, when eta is 0.01, it is progressing along the direction of flight. While when eta is like 10 to the power minus 4, then it's going back, right? And again, one more thing to note is that dynamic model can take a sharp turn, whereas kinematic model definitely will take a little bit of radius, larger radius than the dynamic model. And obviously, this is just the XY view, the top view. Yeah. Overall, I think that's how I will wrap up my presentation. Before ending this, a few things that if some of you are interested in this custom solver, there are until my thesis becomes live and it's available, so you may be able to log into this. Let me open this up. So the CVXGN is one good example. There are a lot of others, but this is one of the good examples where you can actually make an account, log in, and then generate your own custom solver. Like let's say let's log into this, and then you can generate a C code or to MATLAB code, whatever you want, and then you can try this in embedded system as well, I guess. This is one good example of like if you want to try. And of course, like there is a user's guide on what kind of problem you want to solve, if it's a QP problem or the lasso problem, portfolio, MPC. So those of you who are interested, this is really good example. And then beside that, those of you interested in this convex optimization, then this I really like this book. I've been using this for a really long time. This book from Stephen Boy, the convex optimization, and this Vandenberg, both of them. Sorry. So yeah, this book is really good. I mean, well, I have used this a lot of time, and I will recommend those, for especially for undergrad students, even for grad students. Sorry about this. And there's a solver, like other solver like ECOS, which I think you can download it from here. Actually, there are a lot of other solvers developed by this team, by the team of Professor Stephen Boyd. Even CVXGN is here, and I have used this ECOS as well in my thesis so to compare the results, and this is really a good solver as well. Well, there are a lot of competitive QP solvers, a lot more, and if you are interested in making your own custom solver, then there's a paper by the CVXGN as well, paper on CVXGN, how this how this solver, I mean, at least giving you a rough idea how that has been discussed on CVXGN has been made, so at least how to use it or something like that. It has been discussed here, and suppose how to use it, and the example has been given, and then few the information and what algorithm has been used. Sorry, something like that. What algorithm has been used, and what are the approaches, and how do we solve these KKT equations and things like that have been briefly discussed. So yeah, overall, if you're interested, you may want to look into that. And I will also share, I will send this information to Sudhir, and maybe I think he can share this information to those who are interested. So yeah, overall, thank you so much. And that ends my presentation. And Sudhir, you can take over.
Okay, thank you very much, Min. We do have...
Sorry, go ahead.
Yeah, were you saying something?
Shall I stop sharing, or I'll just keep it like this then?
I mean, since we may need to go up and down the slide,
right.
Let's keep it that way.
Okay.
Right, so we do have several questions to begin with. So I asked people to ask either technical or non-technical, all sorts of questions, and we do have some technical and some non-technical questions.
Okay.
So Salim asked a couple of questions, but later he said you've already explained it during your presentation. But I think I did have a couple of related questions. For example, I think it would have, like, on a technical note, I feel like I was looking for a list of symbols somewhere so that I could sort of identify the thing. No, I'm just kidding. Yeah, you don't have to put that in the slide, but just for the sake of doing it. There were the so can you go to page 22? If no one minds, I'm going to start with the questions. So when you are estimating the value of G, the location RB, is that just straight ahead of where you're trying to fly in the line of sight, or can it be somewhere else? Is the gradient of how the terrain changes?
Well, yeah, it could be anywhere. RA and RB is the location of obstacles, like nearby obstacles. It doesn't have to be in line. I mean, in the direction of flight or even in the reference path. It can be anywhere near the UAV. In any direction. Sorry, go ahead.
Right. So, and it can be moving as well.
Oh, yeah, of course, 100%.
Right. Okay. Okay. And in page 35. So for your so delta T values, for larger delta T values, did you tell the algorithm to try and go around if it couldn't avoid the obstacle, or does it do it by some other method?
So no, it's exactly the same. Like the problem formulation is exactly the same. The thing is that when you, so in model predictive control, what happens is that let's suppose we are predicting 6 seconds in future, and we have a 20 node points in between 20 points in between this 6 seconds feature time, right? And let's say we're sampling at 0.2 seconds, and then what happens is that when the UAVs, basically we're going to predict the model, what will be the position of the UAV using this model, like a UAV dynamic model. We're going to predict where will be the position of UAV along that time. And then when this position, when we go like farther away, when the sampling time increases, then the predictions diverges, and then the model itself diverges. That's the reason of failure of this.
Ah, so it's actually diverging. It looked to me as if it was actively trying to decide whether it should
no.
turn around.
No, it's because the divergence of the model. The model
Right.
kind of converts. Like, it's better if it is something like the approximation, Taylor approximation as well. When we are approximating the one nonlinear equation, and if the approximations are really small, then it stays on the nonlinear equation, right? And then if we are taking a really far away apart numbers, then it diverges. The nonlinear part diverges from the linearity. So that's the case.
So what is the trade-off for having the smallest possible delta t? What would keep you from doing that?
So it's a computation capability on board and the size of a problem. So everything combines here. Like, so if you have a good computation capability on board, maybe TX2 are better than that computers, then in that case, maybe like you would be able to solve up to 12 find horizon, maybe with a 200 millisecond of sampling time. Or if you are just sticking for, let's say, if you have pretty much stable UAV, and then maybe you want to, can make stable UAV in the sense that it can make a good enough turns, like 14 or 20 meters of turning radius and things like that, then maybe you should be able to predict up to 10 seconds in future, and then at the same time, maybe 200 to 500 millisecond might work. But if the thing is, how much of agility you want on the UAV, that much of computation capability you need. I mean, the really good computation capability to perform the really agile maneuvers and maybe aggressive maneuvers, and then in the high frequency trajectory generation. So it all boils down to what kind of problem we are solving. So the good trade-off will be like decreasing, like if you decrease the problem size, then you need a low computation capability, but at the same time decreasing the problem size, you may be increasing the sampling time, right? You don't want to increase that sampling time a lot, and you want to remain within the given margin. So these are the trade-offs that you will have to figure out. Think about before implementing.
Right. Okay. So there's some relatively specific questions related to what you talked about, and there are also some questions kind of outside of that. Mm-hmm. I'll actually go to question by Vikas. I'll come to all of the questions one after another, but let me go to a question by Vikas. So does the trajectory generation program, by minimizing the cost function, always generate only one path? If not, how does it choose the optimum path? That's the first question.
Okay, so since it is an optimal control, meaning that we are solving the controls problem using optimization method, and we're looking for optimal, means the best, the one. So for a given specific scenario, specific condition, there should be only one global optimality, right? Global optimal solution. Since it's a nonlinear problem, and definitely, like I said earlier, the starting point matters a lot. So what we are looking here is a local optimal. And locally, we're always getting one solution. But if the scenario changes, if you move ahead in distance, let's say the obstacle changes size and goes on the other side, then you get a different trajectory, definitely. Because that may be an optimal trajectory, meaning optimal in the sense that optimal with respect to the cost function and the penalty parameters allocated. So definitely, it is the optimal, the best solution, but depending upon the scenarios where the obstacles are, where is the imaginary goal plane is, and then the position of the UAV and the current states of the UAV, all of them plays important role. But yeah, it is always the one solution at particular instant, particular moment.
Thank you. So the next part to Bikas's question was, you mentioned about BMS. Can you elaborate on its intended application, range of flight, and weight of aircraft?
Sorry, okay.
Yeah.
Just again, BMS is a battery management system. So that is not part of this research, but anyway, that is something that I worked as a innovation project. Like, it was funded by the SORs in Rajasthan University. I have one more friends on the team. So we're trying to understand how does this lithium ion battery behave, and how can we effectively use these lithium ion batteries on the diverse, like in the grid system, or like how can we supplement the peak load in a grid, or things like that. So it's basically more about the understanding the batteries, learning, like getting the data from that and making a model around it, and then trying to predict how much, like what could the life of the remaining useful life of the battery, like that, so that when you have a second-hand battery coming in, we can predict, okay, this is the remaining life of the battery, and that could be a possible worth of the battery or something like that. So this is a little bit different than this application on a UAV. So I was just briefly elaborating that these were the projects and something cool thing that I did during my universities.
Right. Actually, I think Vikas has another part of the question which may have a pretty interesting consequence, which is when you put a computer like this doing quite a lot of computation per second, does it generate heat that could be a problem during flight? Because that's something I've never thought about.
Of course, 100%. So the Raspberry Pi example is just one example to show that even those kind of computation on board, computer on board can do this thing, right? But definitely you don't, if you have an expensive quadrotor, UAV that will cost you thousands of dollars, then definitely you don't want to put that computers like Raspberry Pi, or maybe you want to opt out for a better one. And along with that, you might you will definitely have to think about the temperature management, heat management. Maybe you'll have a heat sinks and all the things, and maybe air cooling system, because it's a UAV, and flying, so lots of air flowing around. So you definitely want to think about it, and that's something really important to consider, like temperature management, and more important, like along with the temperature management, also the memory management, how you want to manage memory and make sure that you always get at least a solution. Sometimes, like, there may be very few cases that you may not be able to get the optimal solution. Maybe you have to be happy with a feasible solution. When I say a feasible solution, it is a feasible solution, but not the best one, right? So you have to think about the memory management as well. So there are a few other aspects, but the memory management, heat management are also really, really crucial factors in being able to use this algorithm in such computers on board, and then make it actually fly the UAVs around.
Okay, thank you. So Sila Barasan M, I'm sorry if I couldn't pronounce that name properly. Can you explain the test UAV and the hardware setup, like flight controller and onboard computer?
So yeah, I didn't test this thing like on UAV on board, definitely due to the lack of. So here, when it was 2018, I guess, and I was thinking about testing this, then the rules in Canada changed, like especially international students as a foreign nationals being able to get a certificate to test this kind of thing, it became really difficult. And that's why I went for mostly hardware simulation, meaning that I will test it on a real hardware, real computers, and focus on the computational aspect of it, but not trying it on the real fixed-wing UAV. So most of the results are performed, all are simulations, but those are performed on those processors, like ARM processors and things like that, but not on board the UAV now.
Right, okay. So I think that kind of leads to another question, which is the trajectory generation problem more computationally costly, Shovan Rasfesta asks, than obstacle detection system? Isn't that a pretty reasonable question? Why go for a trajectory optimization instead of just avoiding obstacles used based on sensors? And also the second part of the question is, you mentioned Raspberry Pi. Would it be able to solve both of them at real time?
When you say real time, the word real time is like,
I guess like when you're flying.
Yeah, I understand. Yeah, so real time. Sorry, right? So when you say real time, that it means like as if it is happening according to your real clock, right? So that is not the case. It takes some time for you to be able to analyze the situation and solve the problem. And can we use Raspberry Pi on board and the UAV? Definitely. I think like there's a much possibility you can use it. There's a chances that you can actually solve a less complex problem than the one that I showed before. And you may be able to solve the just a trajectory and then fly around obstacles. Second thing is that do we need to solve optimal control problem to avoid around obstacles? So there are other ways where you can solve the problems. I mean, where you can solve the avoidance problems, definitely. The thing is that if in other approaches, there are some other like A star approaches, and then I mean search space and RRT methods, a lot of them. So those are computationally those recently these days these are becoming more computationally cheaper. Like a lot of advancement has been done, but so like if you have multiple obstacles, let's say, and then if you have a scenarios like the one that I presented just now, like you have to remain close to the path all the time, and if you're looking for minimum minimum numerical in the sense that you don't have to add on so many things and if conditions and things like that, rather than you can simply solve that as a control problem, then that would be a lot easier to do than trying out the search space. But definitely this is search space as well, but this is numerically you are going the gradient wise, right? And then solving or getting for the better solution and getting for like one after other solution rather than having searching the whole space. And one more thing is that when we say about let's say other approaches and then just getting a feasible solution. So definitely if you're just thinking about having a feasible solution, avoiding obstacles, like in quadcopter especially, you can just make let's say there's an obstacle, you can stop mid-air and turn left, and then maybe you will go the straight line to you can choose a straight line to the goal point, or even you can go back to the trajectory. But for the fixed wing UAV side, you need to, again, here you can still do the obstacle avoidance without solving this optimal control problem, but you do not get the best path all the time. So what are your requirements if you're looking for a good solution, I mean best solution, or at least locally optimal solution to be able to do those things? Then optimal control is definitely an approach you should go. But if you're just looking for a feasible solution, optimal doesn't matter. If you're gonna fly around just avoiding obstacles, then there are a lot of other approaches. But I'm not sure about the competition time, if I understand correctly. Like a lot of other processes, unless they customize it for the specific application using the general solvers, the solution time is really high. And even for this NLP, without customization, the solution time is definitely higher. I mean, definitely high, right? So you may not be able to solve even within that 200 millisecond of solution time. I mean, like 500 millisecond of sampling time. So I think for any of the, I'm not sure about other approaches. And what I know is that, like, according to my research, those were, I didn't do the best up on the literature review. It seems that those are computationally intensive. That's why I thought, okay, I saw a few papers where this could be, optimal control could be really a viable option given the this customization is possible. And it seemed the customization is possible. And definitely we are losing the global optimality and taking, like, I mean, accepting this local optimality in this optimal control problem. But yeah, there are a lot of other approaches, and you can do that thing with other approaches as well.
Okay, thanks, Vin. So before going to the next question, I think we can stop the screen share based on the questions we have left, so that we can start looking at the presenter finally. Okay. So the next question comes from Samrat sir. In your model, did you consider headwind, tailwind, or crosswind when you're doing it?
Crosswind. Sorry, I am not able to see. Just a second, I am not able to. Okay, here it is. Okay. In this example, I do only have a crosswind, but I did some simulations with the tailwind and not with the headwind. I don't remember doing it with headwind, but I did with the tailwind and a crosswind, yeah. And the example is with the crosswind.
Does it affect the efficiency of your model in any way?
Yeah, of course. So actually, like, it will try to push the UAV out of the, push the UAV away from the reference path. And but the cool thing is that using the MPC approach, that it will try to compensate the disturbances. It's actually within the model itself, it will try to it will try to compensate for the disturbances.
Right. So would you, so if you had to say design something that by default would try to handle a certain level of crosswinds. Would you have to remodel everything from the beginning, or could you just include another parameter?
Yeah, you could simply change the value. That's it in the more given problem formulation. See, this is the thing. When you want to handle the high winds and things like that, no, even the model does not know the wind, right? You can be anything. The thing is that can your UAV, and the first thing is that you should be able to solve the problem like real quick, first thing, because for NPC to be able to like correct those disturbances, or at least try to correct those disturbances to a certain extent, you should be able to solve it real quick. Second thing is that can your UAV do that? Like, does you have the dynamic constant of UAV being able to actually like tackle with that, or at least try to can at least deal with that headwinds, right? It depends on the UAV. So actually, the problem formulation does not know the wind, where it is coming from or how it's coming from.
Right. Okay, thank you. So now I'll start going to more general questions. Deep Ranjan has asked you actually, how can we estimate drag of a vertical takeoff aircraft? Actually, it's a VTOL fixed wing UAV. Do you have any ideas about this?
How can you compute the drag of a VTOL UAV? I think the wind tunnel test will give better results, but not really. Sorry, it's a VTOL UAV going up.
It's a VTOL fixed wing UAV, so I guess the fixed wing part is typically the same as for any other fixed wing aircraft, right?
Yeah. One more thing is that when you're taking vertically off, then the gravity and the air density rapidly decreases, right? And but one more thing is that at the high altitude you might get the winds, and I think it will be like more or less testing it in a wind tunnel. That it depends on the airfoil. The drag is entirely depending upon the area of the air surface, right? So I think it could be something similar, but I am not the best person to answer that question.
Right. Okay. I mean, I think generally this is a very, you have to pick exactly what kind of an aircraft you're talking about. But I think the question mostly relates to a fixed wing that can transition from vertical to horizontal flight. And okay, so the simple answer, as far as if I can answer very quickly, is it'll just depend on what direction you take your flight, and you just change the reference area based on that. And I think it's quite simple when you think about it that way. Okay, so next question is from Rishabh. Can you suggest some numerical optimization problems to start our way in simulation of those problems, or some books where they present problems with simulation codes for beginners?
If you have MATLAB, I think there are a lot of resources available, but those of you who don't have access to MATLAB, okay, I would suggest that if you want to solve these optimization problems like a trajectory generation or even any kind of multidisciplinary design optimization, I think I would suggest you to start with this book, Convex Optimization, and after that, I think there are a lot of references there for nonlinear optimizations as well. And there's one particular book I really like about, there's no code, all theory are there. Theories are there. It's called Nonlinear Programming by Dimitri Bertikas. So this book is something. Let me see if I can.
I think we can type the name in the chat so Rishabh can.
Yeah, and there is one more book by John T. Pitts, the numerical optimal control problem or something like that.
But I mean, this is something I can, if you forward me the name.
Oh yeah, sure. I can do later. Okay.
Send it to Rishabh.
Yeah. Sure, yeah. So there's a nonlinear book by Dimitri Bertikas, but this is really good. That's a more theoretical book, but that has a broad range of like applications, numerical algorithms, not ranging to optimizations alone. That like maybe even for machine learning, and then you could most possibly use that for like training the networks and things like that. I mean, that's a broad book, but for trajectory generation, maybe you want to look into. You're welcome, Lisa. And there is a John T. Bates book by John T. Bates, Numerical Optimal Control Method, or something like that. I'll type both names, and those are really handy. Yeah, I think if you have access to MATLAB, look into that. Maybe AdminCon may not be the best solver, and there are like the solver that I mentioned before. I mean that I just was sharing before. Those are, I think most of them are can solve them. Definitely, the CVX can solve the nonlinear problems as well, and those are freely available for academic purpose, and you can make use of them as well.
Okay.
Yeah, and
Brilliant.
I
So
think
we
you.
are.
Sorry, go ahead.
We are approaching the end of towards the end. So there's like 3 questions left. I mean, if you don't mind, I'll quickly go through them.
No, I can answer. I can take time. That's okay. I can take longer. That's okay.
So one question from Silam Barasan was, what obstacle detection sensor did you use in your testing? Even for your computer model, you must have decided some kind of a sensor, right?
Okay, that jumps into the stereo vision that you can see the obstacles this far, and then you can at least see the surface of an obstacle. Like, okay, here is an obstacle, and then at that distance there's an obstacle, and then you model obstacle around it, and then make a shape around it, and then you model that mathematically, saying that okay, this is the reason you don't want to enter. One more thing I want to if some I want to share is that beside having the obstacles robustness function, that meaning that you don't want to enter into the obstacle in the cost function, I do have the obstacle constraint, meaning that I will model obstacle and say that okay, I don't want to enter into the region, and that becomes a hard constraint. It's an inequality constraint. So cost function is you want to minimize it. There is no hard and fast rule. But the constraint, you have the equality or inequality constraint, something you must satisfy, right? So I have that obstacle avoidance constant as an inequality constraint, meaning that you don't want to enter into it. So yeah, again, so I'll do the same like stereo visions, hoping that like okay, this is a surface and obstacle. I'll model obstacle around it, and then the obstacle of avoidance will happen.
Right. Okay. Well, okay. Let me go through all of the questions. So there's a general question by Nishant, to which I'll come at the very end, Nishant, if you don't mind. There's a question from Abbas Bandari. Will it be easier for a swarm network of UAV to solve these problems and come up with an optimal trajectory?
That's amazing question, because I I was thinking to share that thing as well. That was part of my research, but I thought that presentation was a little bit longer. That's why I did not. But definitely yes. So there are 2 approaches. Like when we say solve for the swarm of UAV, and if you want to solve in a single computer, then the good, like in my experience, that if you solve the entire swarm problem, let's say you have a 32 UAVs, 64 UAVs in a swarm, and if you want to solve the whole problem at once, then it may be too computationally intensive, and you may not be able to get the solution within the required amount of time, right? Let's say within this 200 milliseconds, 500 milliseconds. But if you solve iteratively, like one UAV at a time, meaning that you solve for one UAV, thinking other UAVs as an obstacle, and then you jump to the next UAV, and then think all those UAVs as an obstacle, and almost all the UAVs have all independent controls, and then all of them, they have a different, let's say the flight path. Not flight. The reference path, and all of them, they differently face the obstacles, other kind of obstacles. That's 100% possible, and then there's a higher chances that you may be able to solve that in a good computer. You may be able to solve the problem. Let's say in my computer, I was able to solve the 32 quadrators problem, swarm problem, within less than 200 milliseconds. Again, in my laptop computer, not Raspberry Pi, but in my laptop computer. So I was able to do that. So yeah, of course, you can do that.
Okay, so the next question is from Abhi's Khanal.
One more thing. Sorry,
yes.
sorry. One more thing. Yes, so that was possible only due to this custom solver, not the general solver. Okay, then go ahead.
Okay. So did you do simulation using SITL of open source autopilot like ArduPilot PX4 or MATLAB?
It was entirely on MATLAB, not autopilot. Now, it was on a pipeline to do it, but yeah, I didn't do it now.
Right. So on that, right, how difficult or easy is it for someone to integrate, for example, these kinds of optimization algorithm with PX4 controller, for example?
Awesome. Okay, it's very much easy, and actually, you can even put that in Arduino, not even in a good end computers. So those custom solvers that I said, right? So basically, if you have a program written in C or CPP, and if your problem will pass those information, the Hessian gradient, Jacobians, all those to the custom solver, then it is embedded solver. So meaning that you can keep that on any embedded systems, and then you can even actually run that. It's a C code. You can just plug and play. You can just simply copy the code, put it down there in your folder there where you want to use it, and make sure that the problem is meaning that the solver is customized for your problem. Then you can do it. It is very much simple, and you can use it. And one more thing, like if you want to try it out, like if you want to, one key difference between the CVXGN and the custom solver that I made is CVXGN was geared towards, like, definitely it could do better, I guess, but as of now, like whatever is available to the public, it is targeted for small QP problems to be solved real quickly, whereas the custom solver that I made is for large problems to be solved in less amount of time. So that's the only key difference. And if you want to try it out, you can try the CVXGN, generate the C code, and then copy the C code into your embedded platform where you want to try this thing out, and then see if it works. And if you have any trouble, any issues, you can let me know. You can shoot me an email all the time.
Right. So connected to that, right? So I don't know if Autopilot has been phased out already or whatever, but with the mission planner that they had, could you use, like, if you provide a mission profile, could you use an algorithm of avoiding obstacles, like the kind of algorithm you have? Is it integrable with any open source platforms that you're aware of?
So I think when we pass those goal points and then the reference path and everything, if we write let's say let's write a small piece of software program to the Autopilot and then put it into the system, and if we make use of our algorithm on that Autopilot, then definitely it could be possible. But I haven't tried it out, so any suggestion, I am not the right person to give a suggestion here again. I think it's possible, because if the Autopilot is programmable, I believe it is to a certain extent, and then if it is programmable, then you should be able to do that thing. And I hope they have a and one more thing, that you don't need 1 megabytes of space for storing the solvers. So usually less than kilobytes, then you can be in less than 300, 400 kilobytes of storage is good enough, depending upon the definitely complexity, the size of the problem. But yeah, even less memory is good enough for storing the solvers.
Okay, I think that's about it for all the technical questions. I'll come to Nishant's question now. So what kind of advice will you give to a future PhD student? Because Nishant, I believe, is going to do PhD very soon. And can you please relate to your experience on the intellectual challenges that you faced doing your research on UAVs?
First of all, you need to do a lot of readings. I'm not a fan of readings. I will usually, for me, I definitely will have to go through all those. There's no fast track kind of thing. So you'll have to do a lot of literature review. You have to understand what's current trend. And the thing with PhD is that the challenge you will face mostly, especially here in the US and Canada, is that by the time you are done with PhD, your things become, the things that you are researching does not become really new thing. It gets the things of the past. And because you're taking some time to do it, and a lot of people have been talking about it, you will see some journal conference papers brought it out, and then a few advancement being done. And I think the really important thing to finish your PhD degree on time is to make sure that you make a publication on time, which I did mistake. I should have done real quick. There are a few things I should have improved, I would say. And spend it's really difficult to give time to everything. The problem with me was I was trying to do a lot of things in the same given time frame. I wanted to do so many projects at the same time, do the coursework, finish this, and do research, and then same time try to make sure that I stay ahead and of the track. On this research track, and then I complete my milestones. So focus on your milestone first, and then some publications. And in the meantime, if you have time, definitely go for other projects. It won't be challenging. Else you'll be facing it. You'll get really less sleep during the PhDs if you're doing other projects.
Okay, so Nishant, the general suggestion is publish as fast as you can.
Yeah, right.
And publish as many papers as you can.
Yeah, as many journals as you can, as many conferences where you go, like, where you could go, something like that.
Okay. So I think we have a last question from Abhimanyu Khadka. As a second year student of aerospace engineering now,
Mhm.
just starting to enter our core subject matters, what would be your suggestion to the students? How can we gradually develop our knowledge in the field of UAVs in context of Nepal,
Okay, amazing.
not context of Canada?
Okay.
Make a distinction.
So, okay, in context of Nepal, so I personally think that Nepal is a good testing ground for the UAVs. We as in Nepal, like, we may not be. I don't think, like, when I was a kid, I told my dad that someday I will start a UAVs or like aircraft company in Nepal. Now I feel so ashamed. I was too ambitious at the time, but anyway. At the present context and even in the future, I think the UAVs has a good prospects in Nepal. And for as a student in Nepal, I think it's better that you all the physics, all the mathematics that you go through in your course and I mean in the college program, try to see that as if you like you want to implement that and how you can implement them. If you grasp those things, like how every time you learn new things, and then if you try to think that, okay, what are its implications, like how could you use them, then you will have better understanding, and you don't have to, like, you don't have to look into a lot of the experiences, like intellectually, and just looking into it you can see how those things could be implemented. First thing. Second thing is, definitely you will have to always keep constantly searching what's existing in the market, the worldwide, because now this is not only about Nepal, it's about the whole world. A lot of people do different things, amazing things around the globe. So you may want to look into that. What are people are currently doing? What are they looking ahead? And usually most of the technology are driven by the economics. So you may want to look into that, but don't get overwhelmed by everything that I said. It takes time, and like maybe it takes 10 years for you to grasp all those understanding, and then, okay, this is something we could do in Nepal or things like that, right? And everything that you do as an industry has to be economically viable um, within the country as well. So overall, I would say that stick with what you are doing and trying to see what you could make use of those things that you have read, and then always do some small projects, and that will keep your like knowledge fresh in programming on using those electronics. And see, I'm really a fan of control system. I'm not a fan of, like, it's not that I don't like it, but I don't really enjoy on doing this aerodynamics thing. I really enjoy doing controls and this something that which looks more lively to me, but it depends, like, what are your interests, right? So it doesn't matter whatever interest. Always, like, working in a team is great if you have some friends whom you can work in a team, and the different people looking different things, and then making small projects. Doesn't matter what. If you want to do robotics, if you want to do UAVs, other things, softwares, doesn't matter what. Always keep doing, like, some small projects. Maybe that may turn out to be a startup after a couple of years if somebody sees values in it, right? Or you may even add some value to that and make it as a startup. That could be a motivating thing, and maybe you could use that in context of Nepal. So yeah, I think I should not speak more than that about it.
Okay, thank you. So just to put it out there, aerodynamics is also an interesting subject. Let's not.
Of course.
This is not a competition. Just putting it out there. Okay, I think that's pretty much all for the question. I hope I've attended to all the questions that were put in the chat box there. I will actually leave it to Mr. Ashish Mananda to close the session here. And yeah, I think that's all from my side. Thank you. Thank you, Min.
You're welcome, Day, and thank you for coordinating.
Yeah, thank you, Suleep, and thank you, Meen. Yeah, thank you, Suleep, for moderating the session very, very well and very interestingly. And thank you, Meen, for enlightening us with this insightful webinar. Yeah, thank you very much, Meen. I'm very proud of you, actually, and I wish you all the best. Yeah.
Thank you, Day. Thank you so much.
I think Sudeep, yeah, you missed one question. Like,
oh, did I?
Yeah, from there's this Roji Gupta. Like, thank you very much, sir. We could see the, like, just scroll. It's around like 7:44 p.m.
Oh yeah, so I think there was, it's more of a remark than a question.
Oh,
I think
okay.
the attendee found the topic a bit too challenging, but
Oh.
so let me put it out there that we'll, in the coming weeks and months, we'll have many different kinds of presentations, and this presentation in particular was a scholar series, which means you will be dealing with research scholars, and you'll have to deal with the kind of technical work that research scholars do. And so there can't be any way around it, unfortunately. You will have to dive into the topic, and you'll have to dive into the conversation as well. So, but in the future, actually, before I close the session, we have another presenter, Dr. Richard Glassog from University of Nottingham in UK. Not that your presentation was not really good already.
That doesn't matter. That I'm trying my best to. I'm trying my best to present. That doesn't matter. That's okay. There's always a learning, right?
I'm just trying to pitch our future presentation. So we'll have another presentation on September 4th. I'll put out the ads today itself, and you can start registering. So it'll be about UAVs, air race, the kind of projects they are doing with Airbus, trying to convert our propulsion systems into electric propulsion systems and hybrid propulsion systems. And I think it's going to be a very interesting as well as relatively non-technical discussion. And yeah, you guys feel free to join in that presentation as well. Thank you for attending, everyone. I'm going to close this session now.
Okay.
Sure.
Yeah. Thank you. Thank you, everyone. Right?
All of you. I feel really great. Okay, last, I just want to say thank you to the Astronautical Society and also the co-organizer at the Polytechnic Engineering campus. And thank you for giving me an opportunity to share my, share my work. And I feel in upcoming days, if there's something interesting, if anybody would like to learn about it, I will be happy to present more. And maybe I'll learn by the time to make the context more simpler and presentable to almost all the audiences. Thank you again.
Yeah. Min, you're on for the swarm UAVs for the next time, right?
Oh yeah. Sure, I'll talk about the swarm of UAVs next time.
Okay. All right. Thank you, everyone.
Thank you, everyone. Thank you, Sudeep. Right? Bye.
Thank you.